Hello, welcome to session number 3 in the series System Design. My name is Anurag Nigam and we are talking about system simulation in system view. So let's proceed. So earlier what we did in session 2 was we generated the QAM signal, and in this session we are going to demodulate that QAM signal, and then we are going to compute EVM and bit error rate. Right, so let's go ahead and do that. So I'm going to launch system view, and the idea is the same, but this time I'm going to use QAM 64 rather than QAM 256 for some reasons, like filtering is very stringent, so here filtering is a little relaxed. So I'm going to go ahead and create a new blank workspace, and I am going to rename this design and call this as QAM 64 system, right? And I'm going to similarly rename the rename the data flow controller, right? So I'm going to rename that. So this analysis would be same QAM 64 analysis, correct? And here I'm going to go ahead and change the design to reflect, so change this design to reflect the current design. And here I'm going to say the sample rate is 2 megabits per second, and rest of the things I'm just going to leave blank, right? Same. Okay, I'm going to save the workspace here. I'm going to save this as QAM 64, and that's it. And very quickly I'm going to repeat what I did in session 2, and I have explained in session 2 what those are. And so what we have is a random bit stream. We call this as bits, and I'm going to just place this bits over here and make sure that this is going to not repeat the bits sequence every recalculation, and say okay. So that's your bit sequence. Then I'm going to put a gray encoder in here, and I am going to code 6 bits this time rather than 4 bits. So 6 bits will give you QAM 64, so 6 bits. And then I'm going to have a mapper, so that's a mapper, and here I'm going to just put in a mapper here, and this is a QAM 64 modulation, so I'm going to put QAM 64. So that's done. Next, what I'm going to do is, here I'm going to take complex into rectangular, so I will take complex to rectangular here. Okay, so complex to rectangular, and this will convert it will give you a I and Q channels, and then I need a filter, so I'm going to design a filter. So that's filter designer. So I'll just double click this, and I have a race cosine filter, and here I'm going to put sample rate, right? And here I'm going to put sample rate by 6, sample rate by 6, and here I'm going to have a roll off of, let's say 1 or 10%, and the roll off nature is square root. Again, the length of the filter I'm going to put as number of taps as 129, right? And this is a rectangular window, I'll leave as is, and I'll say interpolation 5. That means I'm taking 5 samples per bit, and I'm going to look at their response of the filter. So that's the response of the filter, right? So everything looks okay to me. Okay, so this is a rectangular window, so I'll say okay. So that will give me the filter. Of course, the symbol rate is kind of a function which is not good to look at, because this is going to be 2 megahertz divided by 6, right? So that's a very strange number. So for changing that, maybe here I can change this to 1.8. How's that? Let's see what happens to that number. Okay, so we will redesign this. Okay, so we will redesign this because that was a irrational number. So I'm going to redesign this. Here the sample rate is 1.8 megabits per second. So that will be sample rate. Here it will be sample rate by 6. Sample rate by 6. Access or roll off as, let's say, 10%, and nature of roll off is a square root. Yes. Again, here it is number of taps I'm going to use as 129, and then I have a rectangular window. Interpolation, that is oversampling, is 5 bits, right? And here I'm going to just compute this and say okay. So that's fine. So now everything looks okay, and now I'm going to just repeat this filter for both the channels. So Control C, Control V. So just bear with me. Okay, so that's the channel filtering, right? And then after that I'll give it to a modulator. So I'll look for a modulator. Okay. Oh, modulator. Okay, so I have a modulator here, and here I am going to set the carrier frequency to be 2.5 gigahertz. So this form of modulation is remaining IQ, and this is 2.4 gigahertz, for example. 2.4 gigahertz, sorry, 2.4 gigahertz. So here what you get out is going to be your QAM 64. So let's have a look at it. So I'm going to put here a sync, and I'll call that sync as, what do you want to call it, TX bit or transmit bit, correct? And so basically that's okay. That's only for the constellation. And then I can put here a spectrum analyzer to look at the spectrum. So that's a spectrum analyzer here, and I will call this one as spectrum, correct? So this is something which we have done last time. It's just that instead of QAM 256 I have here QAM 64. Okay, so let's go ahead and compute results, and then say add. So if everything is okay, I should see a constellation here. So I'll go to add graph, and I'll go to constellation and TX bit, and here I have to specify my decimation factor is 5 and the delay is 64, which is half the filter length. And here I am going to put scale as -2 to 2, and here I am going to also put -2 to 2, -2 to 2. Okay, so that's not so good. Okay, let's just verify if things are okay. Let's go to filter, and here let's put this roll off to no, and here put the roll off to no, square root, and run this and look at this graph. So this is QAM 64. Okay, let me just label this. Okay, so this is a TX constellation, right? And I will call this as output constellation. Okay, fine. Now there is something wrong with the plotting, because you know this roll off, okay, should not matter so much. Access bandwidth is only 10%. Anyways, so that's the output. If I do 5%, that will be much sharper, right? So let's create another filter here. Filter design, and let's make another filter here. Race cosine filter, sample rate by 6, correct? Sample rate by 6, and here access bandwidth, let's say, is 6%. Okay, and say square root, and that's fine. And here I say number of tabs 129, rectangular, and interpolation factor is 5. Say okay, and this, I'm going to replace these. Okay, and then look at the results again. C, Control V. Okay, let's simulate this again. Let's look at the results. Slightly better, but not much better. Correct? Okay, so this is QAM64. And then I'm going to put the demodulator, right? So I will go to demodulator. Okay, and this demodulator, I'll start from here. Okay, and this demodulator, the center frequency is 2.4 gigahertz, same as the modulator, right? So let's see, same as the modulator, 2.4 gigahertz. And this output, okay, or this output is going to go to the input here. Fine. Okay, so this demodulator is done, and then after that I'll take these two channels and put the same filters but with decimation this time. So I'm going to go here. Okay, so that's fine. Here I'm going to put a decimation of 5. So interpolation is not there, decimation 5, and decimation delay is 3. Similarly here, decimation is 5, decimation phase is 3. Okay, so now we have the IQ channels, and then so they are basically just doing decimation, right? Now next is going to be something which converts rectangular to complex, right? So that will give me a complex out here. That's going to give me a complex out here. Okay, so this is done, and after this I am going to put here a mapper or demapper, and this is going to give you the bit stream as the output, the X in the complex, which is I in Q, and this modulation is QAM64, correct? So mapper is configured as QAM64, and demapper is also configured as QAM64, and then I have a gray decoder, and this gray decoder is going to take this output and going to convert the gray code back to your bits, and it is using 6 bits and MSB first. Similarly, this is 6 bits and MSB first, right? So this is done, and after that I will have the output bits. So I will put sync, and here I am going to put here RX bits, right? So, or you can say this is going to be output bits. I think output bits is already named, or what? Let me see what is the name here. This is called TX bits. That's fine. So this is your output bit after demodulation, and that's it. So let's look if I got the bits here, and plus I want to see what I transmitted. So I will put another one over here, right? So another one I will put over here and call this as input bits, right? And so this sync will be giving me input bits, while this sync is giving me output bits after demodulation. And these are the ones which are being sent. So the first order business is to find out what delay it has gone through once you go through this transmitter receiver, right? So there is no RF. So RF basically is going to sit here, right? So this will be the transmitter, the channel, the receiver, and once the receiver output comes here, it is going to be going for demodulation. So right now this is the ideal, path here. So later on we will replace this with our transmitter and receiver and a channel model. Okay, so once we are done with this, okay, so I'm going to plot input versus output bits, but here I need to determine delay, right? So if I want to determine delay between the two streams, which basically accounts for the delay through this entire modulation demodulation, I would have to use something called correlation blocks, right? CORR. Let's see if I find that. Autocorrelation, cross correlation. Correct. So this is the cross correlation, which will tell me how much delay it has gone through, the signal has gone through. So I'll take this and put it over here. Okay, this delay will not, this delay which this one informs will not have the decimation phase delay. So I'll have to add that, and yeah, so I'll have to add some more delay tokens to match exactly the input output. So now another thing I want to do is I want to look at sync. That's the sync, and this one I want to look at the correlation function. So I'll say this as a cross correlation function, and here I'm going to see how many samples I have to delay, correct? And this node basically gives you the delay. So I am going to put another sync here, and I will call this one as delay. It will also giving me output as samples. So this will be a delay between the two signals, and that I am going to see through this cross correlation. Okay, in cross correlation, correlation length I can keep as 1000, start lag 0, stop lag. So how many bits I want to look at? Let's say 500 I want to look at. Okay, so that's done. The thing is normalization unbiased. Okay, fine. So this is done, and this will give me cross correlation between two bit streams. So if I simulate this, okay, and then I go to the data set and look at cross correlation, which is over here, and I'm going to just plot this. So I'm going to just say add graph, new graph. So I'm getting these bits, these which are going to repeat. So this is okay. So of course don't worry about this, but look at it has gone through 150 bits, right, which is the delay before there is a strong, like, so the two signals are differing by 150 bits. Okay, so here I am going to insert some delay to look at it, right? Where would I do this? Okay, here I will insert a delay. So let's plot the input and output bits first. So I'm going to go ahead and add a graph, and here time, and I'll plot input bits versus output bits, and I'll just look at it and I'll just zoom in. Of course, you know, they don't match, right? They don't match, and I need to insert a delay. So now I want to do one thing. I can take this graph, and I can, because the graph is from 0 to 1, so let's add 1 to this and minus 1 to this, so it will split the two waveforms into two graphs, and say okay. So now you see here the blue one is the output bits and the red one is the input bits. So I'm going to delay the red one to an extent that it is going to somewhere find the correlation. So if you can see over here, this is basically the delay. So this is the start of the input bits, but over here this is the start. So once I put the delay, so this is going to align with this one here. So here there will be a delay block in here, delay, and here I'm going to insert the delay here. Okay, so here I am going to put in a delay which is close to 150, let's say 160 here, additional delay due to the decimation phase. Okay, so now if I was to run this again and look at this graph, so this graph, now you see that these have aligned here, right? So now I can put one on top of the other. So basically I can get rid of this plus and minus 1. Okay, so now here you can see they have almost lined up. Okay, they have almost lined up here. So now I know how much is the delay in the path. The delay is 150, right? So let's rename this graph. Okay, timed bits, and graph title is input and output bit stream. Okay, so basically this is your input and output bit stream, and they have lined up nicely, right? So by adding delay, now I'll be able to do bit error rate and EVM. So here I am going to go ahead and add a bit error rate, and here I am going to pick up this one, and then I am going to look at the start point in samples, and let's say I leave first 400 samples because you know the delay plot is accounted for. So here I would say sample start 400 and everything remains the same. Here I am going to insert, so I'm going to compare, right? So this is the one which I have to compare. This is your output bits. Okay, doesn't matter. So this is your output bits, and this delay I'm going to put back as 150. You know, forget about the decimation kind related delay. And here I am going to just hook up here, and this will give me bit error rate. So I'm going to hit simulate. So now you can see here no errors have occurred yet. So basically if I go here in this, and if I look at B2, which is your, so it says that 0 bits are in error, right? So that means that whatever I have sent through this envelope upon demodulation gives me no error. 0 bits are in error here. So that's one part. Next is the EVM part. So here I would put here EVM, and EVM over here I'm going to look at the complex signal rather than the envelope. Okay, and here I would say I have left first 400 bits, so sample rate, so that's first 400 bits I have left, and then symbol rate is sample rate by 6, right? And result length I'm going to put here, let's say 2000, and the modulation type is QAM64, measurement filter as none, reference filter is rectangular, and that's it. So once I have done that, I'll connect here, and I'm ready for EVM simulation. So this is a very simple setup for EVM simulation, and I would just say simulate. So it just says we didn't have any bits in error, and here if I go back to my data, I have E1, and this is 1.5% as EVM on that constellation. So the constellation is over here, so this is that. Okay, so something wrong with the plotting of constellation. So let me just change my filter to have access bandwidth of 10% and then look at the numbers, or maybe 20% and look at the numbers. So here let's design this filter again. So I'll go to filter dash filter design. So don't worry about the plotting. So the plotting is basically there has to be a decimation issue here. So there is a decimation issue here, that's why it was giving you a problem here. So let's design the filter with a 10% bandwidth. So I go here and say sample rate, and here it is sample rate by 6. Access bandwidth is, let's say, 20%, and raised cosine yes. Phase equalization, okay, number of taps is 129, right? And then window is rectangular, interpolation is, let's say, 5 bits, and say design and say okay. So I have a filter. So the problem is the way I'm plotting the constellation, it doesn't account for the decimation delay. That's why that is scattered. So I am not going to worry about that for now. Okay, so this is with a 20% excess bandwidth, and here I am going to replace this with a decimation of 5. So I'll just copy this over here, and here I am going to put a decimation of 5 and decimation phase of 3, and I am going to just repeat this over here, and we are all set. So I am just going to run this. Okay, so let's run this. Okay, so let's look at the numbers again. So it's like 0.2% EVM here, peak EVM is 0.58%. So now this is a good signal source, right? If I want, I can plot the constellation, the spectrum here, right? So let's add a graph. The transmitted spectrum was spectrum power. Okay, so this is the spectrum which was transmitted, and then I demodulated it and received my bits and the correlation delay. So this is power spectrum, time bits. So correlation delay here was at 150, and I went ahead and put that delay over here of 150, right? And then I looked at the bit error rate. So in the result, my bits are not received in any error, and with the EVM of 0.268%. Okay, so this was a very simple exercise. In the next session, I am going to talk about the RF portion of the chain. So here the output will go into a transmitter, go through the antenna through a channel, and then be received by a receiver, and over here the receiver output will go into demodulator. So rest of the blocks will remain the same. So I'm going to analyze this transmit receive chain in the another form of analysis, which is called spectrosis, so which is called RF system analysis over here. So that's for the next one. Thanks a lot. Thank you.